What if I told you that the entire scientific revolution, from discovering gravity to landing on the moon, rests on just 5 basic rules? These rules are not just for scientists in labs. They define how we uncover the secrets of the universe. Let's explore how these simple yet powerful ideas guide every experiment, every discovery, and every breakthrough in science. Our first stop on this journey through the cosmos of scientific thought brings us to the very foundation of knowledge itself, empiricism. It's a rather fancy word for a straightforward idea: seeing is believing. Imagine you're Galileo Galilei staring up at the night sky. For centuries, dogma held that the heavens were perfect, unchanging. But Galileo, bless his curious soul, he didn't just take anyone's word for it. He pointed his newly crafted telescope towards the heavens, and what did he see? Moons orbiting Jupiter, blemishes on the sun, imperfections that challenged the very notion of celestial perfection. That, my friends, was empiricism in action. Empiricism is the bedrock upon which we build our tower of understanding. It's about rolling up our sleeves and getting our hands dirty, measuring, observing, gathering data, and letting the universe speak for itself. Turned out to be a scientific mirage. Now let's talk about a concept that often trips people up: falsifiability. It sounds like a mouthful, but it's actually a rather elegant idea. It means that for an idea to be considered scientific, it has to be testable, and more importantly, it has to be disprovable. In other words, there has to be a way to prove it wrong. Let's take an example. Imagine someone claims they can talk to ghosts. Now that's a fascinating claim, but how do you test it? If the ghosts don't feel like talking on a particular day, does that disprove their existence? Or maybe the ghosts are shy and only communicate through vague feelings or flickering lights. You see, without clear, testable predictions, the claim of talking to ghosts becomes impossible to prove or disprove. Now let's contrast that with a scientific theory like Einstein's theory of general relativity. Einstein's theory predicted that gravity could actually bend light. Scientists were able to test Einstein's prediction during a solar eclipse in 1919, and guess what? They found that starlight did indeed bend around the sun, just as Einstein's theory predicted. We now arrive at a cornerstone of the scientific method, a principle that separates genuine discoveries from flukes and wishful thinking: repeatability. In essence, it means that for a scientific finding to be considered valid, it has to be reproducible by other scientists in other labs under similar conditions. Think of it like baking a cake. You find a recipe that claims to make the most delicious chocolate cake in the world. You follow the instructions meticulously, measuring each ingredient carefully, baking it at the precise temperature and time. But when you pull it out of the oven, it's a disaster, a flat, burnt mess. Now, you could conclude that the recipe is flawed, that the claim of the most delicious chocolate cake was a lie. But before you toss out the recipe, wouldn't you want to try it again just to be sure? Maybe you misread a measurement, or maybe your oven heats unevenly. The same principle applies to scientific experiments. If a scientist claims to have made a groundbreaking discovery, but no one else can replicate their results, it casts serious doubt on the validity of the original claim. It's not about doubting the integrity of the scientist. It's about ensuring that the results weren't due to some unforeseen variable, a contaminated sample, or an error in the experimental setup. Repeatability acts as a filter, a way to weed out errors and ensure that only the most robust findings make it into the scientific canon. It's a bit like a game of telephone. One person whispers a message to another and it's passed down the line. By the time it reaches the last person, the message is often garbled and distorted. But if enough people repeat the message, the original meaning is more likely to survive intact. In science, repeatability ensures that the message of a discovery, the essence of a finding, is transmitted accurately through the generations of scientists. Our journey through the pillars of scientific thought brings us now to the fascinating concept of causality, the idea that every effect has a cause, that events are connected in a web of cause and effect. It's what allows us to make sense of the world around us, to predict what might happen and to understand why things are the way they are. Now, causality seems pretty straightforward, right? You drop a glass, it falls and shatters, cause and effect. But the universe, my friends, isn't always so simple. Sometimes the connections are subtle, hidden beneath layers of complexity. And sometimes what appears to be a cause and effect relationship is nothing more than a coincidence, a chance occurrence. Think about the ancient belief that the stars and planets influenced human destiny. For centuries, people looked to the heavens for guidance, believing that the movements of celestial bodies could predict everything from personality traits to the rise and fall of empires. But as we've learned more about the universe, we've come to realize that this apparent connection is an illusion. The stars, as beautiful and awe-inspiring as they are, don't actually dictate our fate. Their influence on our lives is primarily gravitational, and even then it's minuscule compared to the forces at play here on Earth. Astrology, as intriguing as it might seem, fails the test of causality. Now, contrast that with something like germ theory. For centuries, people believed that diseases were caused by everything from bad air to divine punishment. But in the 19th century, scientists like Louis Pasteur and Robert Koch revolutionized our understanding of disease by demonstrating that many illnesses are actually caused by microscopic organisms, bacteria, viruses, and other pathogens. This discovery wasn't just a scientific breakthrough, it was a paradigm shift. It allowed us to understand the true causes of diseases, to develop treatments and vaccines, and to improve public health on a global scale. Germ theory, unlike astrology, is firmly rooted in causality. We can trace the chain of cause and effect from the entry of a pathogen into the body to the onset of symptoms. Now, establishing causality isn't always easy. It requires rigorous experimentation, careful observation, and a healthy dose of skepticism. We need to rule out other possible explanations, control for confounding variables, and demonstrate a clear, consistent link between cause and effect.